Hi everyone, we're just going to go through another problem I've seen with student curiosity. He goes through this problem, but he stops short, I think, by finding only the real root of this problem. M to the 9 plus m to the 6 equals 36. It's going to have 9 roots because it's a 9th order polynomial here. It's also a quickly increasing polynomial, so we suspect it will only have one real root. So we're looking for 8 complex roots, which makes the hunt much more fun. So how are we going to crack this? Well, notice first of all that the 9 there and the 6 there have a common factor of 3. So I'm just going to rewrite that. M to the 3 plus m to the 3 to the 2 equals, and let's speed things up a bit. Let's recognize that 36 is equal to 27 plus 9. So here I'm just going to let q equal m cubed, and then we can continue with a simplified notation. We're going to go q cubed plus q squared equals, come on, we can see that 27 is 3 cubed, can't we? 3 cubed plus a 9 is equal to 3 squared. And straight away we can see that one of the solutions for q is going to be 3. So we have a q1, if you like, is equal to 3. And our first root is going to be m1 is equal to the cube root of 3, because q equals m cubed. So we will find that those are the only real solutions to our problem, and the rest of this video we're just going to find and visualize the complex roots and see how that works. Okay, let's move on. So what we're going to do now is rewrite q cubed, 3 cubed, q squared and 3 squared as the difference of 2 cubes and the difference of 2 squares. So we're going to write q cubed minus 3 cubed as one expression, right? And from that we're going to have q squared minus 3 squared. Okay, and here we can rewrite that as a difference of 2 cubes. We're going to write that as a difference of 2 squares. So the difference of 2 squares, just to remind you, a minus b multiplied by a plus b, and then the difference of 2 cubes, the identity there is a minus b into a squared plus ab plus b squared. You can check that one out if you like, if you want to. So 3 cubed here, we're going to allow us to write q minus 3 into something, q squared, plus 3q plus 9. We add to that the bit here, this one, that's going to be equal to q minus 3 times q plus 3. And we should see then that we've got a common factor that we can take out. Let's do that. Q minus 3 into q squared plus 3q plus 9 plus q plus 3. We can just tidy this up a little bit. Let me just move my board up slightly, and we are going to be able to rewrite that as that is one root. That confirms that one of the roots is 3, because we're going to set that now equal to 0, having moved everything across. So I should have said that earlier on, that having brought the 36 across, all of this is going to be equal to 0. So I did miss out a step there, my apologies. And let's move on up. So now what we're going to do is have q minus 3, that confirms our root, and then we can just tidy up here. We now have q squared plus 4q plus 12 equals 0. So let's now solve this quadratic equation. Q squared plus 4, the square of that would be q squared plus 4q plus 4. So we can complete the square and tidy this up. So we're going to use complete the square here, CTS, and we have q plus 2 squared is equal to, right, the 12 taken to the other side and the 4 added on to the other side when we made this square here. So that's a completing the square step. Let's now go to the next step. Q plus 2 is equal to the square root of -8. We don't like that, so we're going to rewrite that. Q equals -2 plus or minus the square root of 8 times I, where I is the square root of -1, which allows us to process that bit there. Okay, so there we find that we have the two other possible values of Q. Right, let's just write them all out. Q1 is equal to 3, Q2 is equal to -2 plus the square root of 8 times I, and Q3 is equal to -2 minus the square root of 8 times I, or I on the Armand plane, on the imaginary complex plane. So now let's just think about where we're going to be able to see these. This is a real number, okay? It has a magnitude of 3 straight along the real axis. So straight along the real here. I don't know what happened there with my pen. So we could have a 0 there and a 3 there, and we could say that Q1 is there on the real axis, okay? And going up here, we're going to have the imaginary scale there for our complex plane. And the other two, right, -2 and √8, are going to be in a slightly different place. So -2 and √8 is going to be over here somewhere. And the other one, -2 plus √8, or minus √8, sorry, going to be round about there. So that is the real root. That is Q1. That is Q2, and that one is Q3. Now what we have to worry about are what are the values of the m's, because remember Q represents m cubed. So let's proceed down. We'll take one of these and then we'll take a look on Desmos to see what we're actually doing. So let's just bring into the game our idea of complex numbers. So over here we have two complex numbers. They are the complements of one another. And what we want to do is, knowing that that is Q, we'd like now to try and find out where its roots are. The 3 roots that it's got. It has 3 cube roots also. So let's just remind ourselves that if we want to take the cube root of a complex number, z to the power 3, you have to take the magnitude, that is the length of the hypotenuse there, if you like, right? That's going to be whatever it is, the length of that. You're going to find the cube root of that, and then you're going to multiply that by this bit here. This is the cos of the angle that you start from. So in this case, the first of these things is along here. Okay, so cos of 2 pi, all divided by 3, where that is the original angle here. Then we add to that the sine of the same thing again, theta plus 2 pi all over 3. And that is on the imaginary axis. And using this formula, as long as you can work out the value of the magnitude, which requires that we use a bit of Pythagoras, we can work out where it's going to be on the Argand diagram. So let's take a look at all of these roots. We're not going to work them all out. I'm letting the computer take the strain here. So I'm going to go back to Desmos. This particular formula here, m to the 9 plus m to the 6 equals 36. I'm going to tell Desmos that that's the imaginary scale and that's the real scale. And we're going to plot our first root here, Q1. That's the one we found there, which is basically 3. The 3 there is the real component, and here the 0 is the imaginary component. There's no imaginary component, so it's a real number. The other two are spread out into different places. The magnitude of this one is going to be Pythagoras applied to these two coordinates here. And we'll be able to see the circle for Q1 all the way around, and the circle for the other two like that. So we've got Q1, which was nice and easy. That's the Q minus 3 part of the factorization. And then these are the two solutions of the quadratic equation. When we apply the formula we've seen, we can then go through and get solutions for all of the other roots. First of all, M1 is the cube root of Q1 here at 3. So that's the cube root of 3, 1.44225. It's real. It has no imaginary component up here. And then we apply that formula and we can start to place all of the other roots for this particular problem. There are 3 more roots. They are all of the roots of Q1 and they have their own circle. There it is. The next one, the next set of roots are all going to come from Q2, which is set up here, and like that. They too have their own circle. This one is going to be the, here it is, 1.5309. We have on that same circle as roots to the Q3 here, those remaining roots. So there you are. In each of these cases, the real part is the x coordinate and the imaginary part is the y coordinate. You can imagine the letter I in there. And there you can see it. Those are the 9 roots of this particular equation. And if we very quickly pop back out, we can make a little statement. M9 to the 9th should give us 27. And it does. Okay, but you can check for yourself just to be absolutely sure. The same thing applies to all of the other complex roots that we found. So there certainly are the values for M. So I hope you found that one useful. I'll just bring back the more beautiful diagram there from Desmos, and I'll share this file if you think that will be useful. Take care. See you in the next video.